Okay, so on Tuesday, I started introducing this concept of the integrated rate logs. Integrated rate log is another method by which we can determine the order of a component or components in the rate log. Integrated rate log use graphing to determine the order. Specifically, we develop 3 graphs for each set of data. With those 3 graphs, we add a linear trend line, and we look at who gives the best R-squared value, meaning which set of data matches a linear line the best. Whichever one gives the best R-squared data, that is telling us the order with respect to that component. So if you graph concentration as a function of time, and it were to give you the best straight line, then that's telling you that it's 0 order with respect to that component. If you graph the natural log of concentration as a function of time, and that were to give you the best straight line, then it is 1st order with respect to that component. And if you graph 1 over the concentration as a function of time, and that were to give you the best straight line, then it is 2nd order with respect to that component. So again, we make 3 graphs and we figure out which one gives us the best straight line, and that is going to tell us a little bit about the order. Now, once we know the order of the component, we can use the equations for the linear line. So y equals mx plus b. And there's some information that you can obtain from the equation for that linear line. One piece of information that you can obtain is going to be the rate constant. For 0 order and 1st order, the slope of the line is equal to a negative rate constant. In 2nd order, the slope of the line is equal to a positive rate constant. So again, we can use those equations to determine our rate constant. Technically, the other thing you can use the equation for is to determine the initial concentration, because the initial concentration is associated with the y-intercept of them. But there's more information that those integrated rate logs can do. We can use those integrated rate logs for. Once we know whether it's 0 order, 1st order, or 2nd order, we can use the equations to calculate various pieces of information. For instance, we could say on this one, at what time in seconds will we reach 0.5 molar? We can use our integrated rate log to determine that. The other thing that came up is the half-life. And a half-life means that half of the reactant is used up. So at what time does half of the reactant disappear? Sometimes it's going to be one of your points on the line. Sometimes it is not. That's why we use the half-life equation to determine what the half-life of the reactant is. Any questions about my summary leading into what we're going to do today, which is we're going to start by graphing a series of data. From that, we're then going to go back and answer some questions that were posed on the PowerPoint slide. The second practice problem we're going to do is we're going to look at a graph, and we are going to determine some information based off of the pre-made graph. So those are the two practice problems we have. Any questions? Okay. So I have already taken the data that was on the slide and I have input it into an Excel file. On the left-hand column, I have time in seconds. In the right-hand column, I have the concentration of the component at that particular time. First thing we're going to do is we're going to graph this using a scatter plot. And just like we did in the graphing lab, and just like we have done since then, we're going to take and we're going to add a trend line for this equation. Then I always have to go back and get my trend line right. And I am going to add the trend line that has the equation. It's not very visible, but the R squared here is 0.61 something. So that is not a very good trend line with graphing concentration versus time. So it is not zero order, most likely. So we go in and figure out if it is first order. And the way, now I have to do it, I just remembered I have to do it slightly different on my iPad. It is going to be equal to the natural log B1 and when you do graph when you do get the natural log, it is always a negative value, so don't freak out. There we go. And we're going to graph that. And yes, it does take time. So insert, chart, scatter, scatter. We're going to add a trend line. And we're going to make sure we have our equation. And this time our R squared is 0.8948, so it is better. You also have to graph one more. Now on the lab, you'll actually have to turn in your graphs. So you've got to go in and edit the X and Y axis and the chart title and make it all pretty. Here I'm just illustrating. And the third one was for a second order. It is 1 divided by. And so you put in 1 divided by that number and you graph it. And you add your trend line. And you make sure you have your equation. And here we have an r squared of 1. So we know, because it has the best r squared, that this reaction is second order with respect to that component, because 1 over A gave you the best concentration, or gave you the best r squared. So we determine the order of AB. It is second order with respect to AB. And we know it is second order because, again, 1 over A gave you the best straight line. It gave you the r squared closest to 1. Now, if it is 1 over A, that means that the equation we're going to use to do calculations is 1 over A at any given time is equal to a positive KT plus 1 over A of the original concentration occurring at 0. So if we want to predict the concentration of AB at 25 seconds, we're going to use this equation and we're going to solve. So we want to know, what is the concentration at 25 seconds? That is going to be equal to K, which according to our graph was 0.0225, and that is going to have the unit of per molar second, times our time, which is 25 seconds, plus 1 over the original concentration, which was 0.950 molar. And now we're ready to solve for AT. So 1 over AT is equal to 1.615, and that is going to be in per molar. Now you can use your inverse button, which is the x to the -1 button on your calculator. Where's that located? There it is. And what we find out is that our
concentration at the 25 seconds is going to be equal to 0.619 molar.
Folks, just like before, I always recommend you do a check. At 0, it was 0.950. At 50 seconds, it was 0.459. So at 25 seconds, does it make sense that it would be 0.619? Yeah, because it's in between these two numbers. So I always recommend you do a quick check to see if your data makes any sense. Questions? This equation will be given to you. You just have to know to use it if it's second order. One of the key things I will say is in this particular case, we were dealing with a rate constant of molar per second. Per molar second. The time point was in seconds because that was what our time was given to us in. So when I used this number 25, I did so because I definitely needed it to be in seconds in order to match what I originally graphed. If your time that you graphed had been in minutes, then this would have needed, the 25 couldn't have been used. You would have needed to convert that into minutes. So in other words, the biggest issue here in these integrated rate laws is making sure your time unit matches. What is the value of K? Well, again, for a second order, the slope is simply equal to K. So therefore, it was 0.0225 per molar second. What is the half-life of this reaction? The half-life for a second order reaction is that T1/2 is equal to 1 over K times the original concentration. So it is equal to 1 over 0.0225 per molar second times the original concentration of 0.950 molar. So that value comes out to be 46.8 seconds. Again, I'm going to look and see if that makes sense. I know that half-life means half. Half of this is 0.475. No, yeah, half of it's 0.475. So I know it has to be less than 50. Because if it gets to 50 seconds, it's 0.459, which is already less than half, meaning a half-life has already passed. Questions? So what did I do? I made 3 graphs. The first one was concentration versus time. It had a bad R-squared. The second one was natural log of concentration versus time. Its R-squared was better. But it wasn't until I graphed 1 over A versus concentration. 1 over A in concentration versus time that I got the best R squared. So because it was 1 over A, that told me that it was second order. And from that, that is where I came up with this equation, and the fact that the slope was equal to K. I knew those because those are all associated with second order. Questions?
Okay, let's look at another example. Okay, the concentration of A for a reaction, A going to form products measured as a function of time, is shown. Examine the graphs and answer the questions.
Simply by looking at these graphs, this first one
is A versus time. The second one is natural log of A versus time. And the third one is 1 over A versus time. Now, I do realize you're not given the equation.
But just simply looking at the graphs, which one is going to give you the best R squared for a linear line? The second one. So this one is going to be our best R squared
for a linear line. So therefore, this is telling me, the natural log of A is telling me that it is first order. Now, the next question is a bit more challenging. It asks, what is the value of K for the reaction? Okay, so what do we know? We know that for a first order, the slope of the line is equal to a negative K. And from algebra, you know that the slope of the line is the change in Y over the change in X, or rise over run. So the first thing we're going to do is we're going to go to this equation and we're going to pick 2 points. And I like to pick points that it's fairly obvious. It's not going to be perfect in this case because we don't have the calculation, but we can get it fairly obvious. So what I know, I'm going to use this particular point, and I am going to use this particular point. Those look like 2 points that I can tell pretty much roughly the concentration as a function of time. So my slope is going to be Y2 minus Y1 over X2 minus X1. Y2, and I'm going to have to move a little bit, but that's, so Y2 is a negative 4 minus Y1, which is roughly 3.2 2. And that's a negative 3.2. Over my x, which is going to be 175 minus 50. So the slope of this line negative 0.8 divided by 125, or in other words, it's roughly what I just calculated was a negative 0.0064. Since it's first order, or I'll come back to that. The next thing we know, again, is that slope in first order is equal to a negative k. So a negative 0.0064 per second is equal to a negative k. So the rate constant is 0.0064 per second. Folks, some of this comes from algebra. Some of this comes from the fact that this is first order. And we know it is first order because it was the natural log. Questions? The last question is, what is the rate law for this reaction? Well, since it's first order, then the rate would be equal to K times A raised to the 1. Let you take a moment to digest. So you can ask questions. Again, if I ask you this type of problem, show your work, because if I had chosen at 0, I think my number comes out to be slightly different. I think it comes out to be 0.01 instead of 0.006. The reason of that is sometimes the point you pick is not as obvious, whether it's perfectly on the line, halfway between the lines. So I give you some leeway. So always show your work. Questions? Yes.
Like if we get a question like this on the exam, but it looks something like this where we are given graph.
You will, okay, so on the exam, I give you the graph. I also go ahead and basically I make the graphs like I expect you to next week. So they are labeled. They also show the trend line and they show the equation in R squared. So I go ahead and give you all the information, more like what was on the first problem, but I did want to show you. I like this problem because it makes you remember how the slope is connected. So. No, as far as how I expect this question on the exam. That's a good question, actually. Like I said, I'll give you 3 graphs. I'll ask you what's the order with respect to the reactant. I'll ask you, what is the rate constant? And remember, rate constants must be positive value. This one comes out to be positive because the slope, which was negative, was equal to a negative. So it comes out to be positive. I'll ask you to write the rate law. Just like I did in that third problem. I'll ask you to use the integrated rate law for the linear line and determine determine one of the pieces of information. Given the rest of the information. And I'll ask you to do a half-life calculation based off of the integrated rate law. As of right now, I do this test, as you can see, is going to be extensively math, but I know there is going to be one question related to the rate law that you have to explain the rate law, what it means with respect to the molecularity and stuff like that. So I expect that to be a question on the test. You have to understand what rate laws mean, not just how to get the number. Okay. Any other questions? Not, then we'll move on to the effect of temperature on reaction rate. Okay. We started the story about the speed of a reaction by describing things that impact the speed of the reaction. We talked about concentration, we talked about temperature, and both of those were particularly important because we need collisions with the correct energy in the correct orientation in order for the reaction to occur. So 2 things that we generally can increase, and I say generally because typically if you increase one or both of these things, you're going to increase the rate of the reaction. Rarely does a reaction not behave, but it does happen. So 2 things that we can do to generally increase the rate of the reaction is we can increase the concentration and we can increase the temperature. Looking at a rate law, it's easy to see how the concentration comes into play because we have brackets that represent concentration. So the concentration is in your face as to how concentration plays a role in the reaction rate. But what is not very obvious is where is the temperature located? We know increasing the temperature increases the rate, but where is that temperature located? The answer is the temperature is a factor of the rate constant. So up until this point, we just said the rate constant is the slope. Well, but what does that mean? What does a rate constant mean? How is that related to temperature? Well, that's what we're going to look at starting now. So, rate constant. The rate constant K is equal to A times the exponential of negative E sub A over RT. Right here is where that temperature factor comes into play. Now, I'm going to introduce each of these terms that you see in the equation, but then we're going to look at each term in a little bit greater detail. So A is known as the frequency factor. The E sub A in the exponential piece is known as the activation energy barrier. You'll hear me go between activation energy and energy of activation. Same thing, different direction. The activation energy has the units of joules per mole. R, we've actually seen this R before. It is an ideal gas constant. But specifically, again, it is the ideal gas constant dealing with energy. The R is 8.314 joules per mole Kelvin. The R is a dictator. It dictates, which is some folks missed on the last exam. They did not pay attention to R's units on the last exam, and it caught them pretty bad. R is a dictator of units. It is saying that the energy factor has to be in joules per mole. And it is saying that the temperature, which is T, must be in the unit of Kelvin. Yes. This lowercase e is like the exponential on your on your calculator. No, it is the opposite of natural log.
Yes.
Yes.
Okay. Activation energy.
We're gonna spend a little bit of time on this slide, understanding this slide and figuring out what everything is on this slide, because you will have a question related to it on the exam. When we talk about activation energy, we're talking about the pill, the energy, the reactants must surmount in order for a reaction to occur. The larger the activation energy, one of two things. Number one, the less likely the reaction is to occur. And number two, if we're going to make the reaction occur, we've got to supply that amount of energy in temperature to make it happen. Now, these diagrams are referred to as energy of activation diagrams. They have several pieces. The first thing I want you to note is that the y-axis is energy. The x-axis is the direction of the reaction. So in other words, it's saying that on the left-hand side, we have our reactants, and on the right-hand side, we have our products, because the reaction typically goes from reactants to products. The distance in energy between the reactants and the top of that is the energy of activation. It's describing the barrier. Now, at the top of this diagram, at the very, very top, is known as the activated complex. Or in other words, the transition state. Because at the top of that curve, we will have basically the reactants will have done what they need to in order to slide down the other side to get to the reactants. Now you will notice another arrow on this diagram, which is the distance between the reactants and the products. That, folks, it says energy absorbed in this case. That means that that is the enthalpy of the reaction. And in this case, it's going to be a positive value because you had to add
energy, more energy in, you had to add more energy in than you got out. So it's a positive delta H. So this is an endothermic reaction. The other diagram on this has the same components. It has the reactants. It has the energy of activation. It has the transition state. And it has the enthalpy, which will be the distance between the reactants and the products. In this case, we're talking about a negative delta H because more energy was given off than was absorbed. So this is an exothermic reaction. Both of these have a fairly high energy of activation. We're going to talk in a little while, well, probably on Tuesday, how we can try and lower that energy of activation in order to make the reaction more likely to occur by adding a catalyst. Any questions about the energy of activation diagram? We're going to come back to it when we talk about reaction mechanisms also. So we're going to see these again. Now, so that was the activation energy. The height of that hill is the activation energy. What do we mean by a frequency factor? A frequency factor describes how many molecules start the process. Meaning, how many molecules start to climb this hill? The more molecules that start to climb this hill, the more likely we are to actually get a molecule to go over the hill. So the larger the frequency factor, typically, the more likely the reaction, the better our chances of getting this reaction to occur. So again, it's simply the number of times that reactants approach the top of the activation energy barrier. Not necessarily surmount it, but approach it. That is what A is. That is what the frequency factor is. Describes the number of times a molecule approaches the activation barrier. Now, let's go back to that exponential factor. Again, what we're talking about when we're talking about this E is we're talking about the inverse of the natural log. This exponential factor, negative E sub A over RT, this will be a fraction. This will be a number that comes up between 0 and 1. And basically, it represents the fraction of molecules that actually have the amount of energy to surmount the activation barrier. So in the previous slide, I introduced the frequency factor A. That is the number of molecules that approach that activation barrier. This exponential piece describes the fraction of molecules that actually reach that activation barrier and can go on to the product side. Okay. You haven't noticed? Yes. When we develop a graph, we can do exponential. I mean, that's one of our buttons that we can hit on Excel is exponential. But what do we prefer? Linear. So, how can we take the rate constant equation that I gave you on the first slide and graph that to obtain a linear function? That, folks, is the Arrhenius plots. An Arrhenius plot allows us to better understand the kinetics of a reaction with respect to the energy of activation and the frequency factor. The way you get this is you take the natural log, which is the inverse of the exponential. You take the natural log of the original equation. When you take the natural log of the original equation and rearrange, you get the natural log of the rate constant is equal to a negative energy of activation over R times 1 over temperature plus the natural log of our frequency factor. Or in other words, we get Y equals mx plus b. So in other words, our slope here is going to equal a negative E sub A over R. And our y-intercept on the graph is going to equal the natural log of the frequency factor. And we obtain these pieces of information by plotting the natural log of the rate constant as a function of 1 over the temperature. So let's look at some practice problems. The rate constant of a reaction at 32 degrees Celsius is 0.041 per second. If the frequency factor is 1.4 times 10 to the 13th per second, what is the activation barrier? So we know that the natural log of K is equal to a negative E sub A over R times 1 over T plus the natural log of A. That's the equation, and yes, you'll get this equation on the exam. We know K is equal to 0.041 per second. By the way, out of curiosity, can anybody tell me what order this reaction is with respect to that reactant? The rate constant tells me it's first order because the rate constant's per second. We know that T is equal to 32 degrees Celsius. Which means it is 305.15 Kelvin. We know that the frequency factor A is 1.4 times 10 to the 13 per second. And in this equation, we know that R is a constant. It is 8.314 joules per mole Kelvin. So we have all the components in order to solve for E sub A. So plugging everything in, the natural log of 0.041 is equal to a negative E sub A over 8.314 joules per mole Kelvin times 1 over T in Kelvin of 305.15 plus the natural log of 1.4 times 10 to the 13. The left-hand side is a negative 3.194. That's equal to a negative E sub A over 8.314 times 0.00328 plus the natural log of 1.4 times 10 to the 13, which is 30.27. Rearranging this equation, and solving, you get a negative 84,823 joules per mole is equal to a negative E sub A. So our E sub A is equal to 84.8 joules per mole. I meant kilojoules per mole. Automatically change it in my head and forget to. Kilojoules per mole. So what did they, oh, so let me explain some of this math. First of all, from reactants to the top of the curve, the difference between that is 84,823 joules, or 84.8 kilojoules per mole. The frequency factor means that 1.4 times 10 to the 13 molecules approach the top of that. But only a fraction of them will get over the top of the diagram and make products. At this, and again, this is all temperature related because rate constant is dependent upon the temperature. Questions about meaning? So let's look at another one. The rate constant for a reaction was measured as a function of temperature. The plot of natural log of K versus 1 over T is linear and has a slope of negative 1.85 times 10 to the 4 Kelvin. Calculate the activation energy for the reaction. If you think about our equation, the natural log of the rate constant is equal to negative E sub A over R times 1 over T plus the natural log of A, with the equation being Y is equal to mx plus B. So if we say our slope, M, that means that the slope is equal to a negative E sub A over R. We're told that the slope was a negative 1.85 times 10 to the 4th Kelvin. So that's equal to a negative E sub A over 8.314 joules per mole Kelvin. So doing the math, (1.85 to the 4th times 8.314), you get an E sub A equal to 153,809 joules per mole, or in other words, the E sub A for this reaction is 153.8 kilojoules per mole. So what that means is from the reactants, the base of the reactants to the top of the hill is 153.8 kilojoules. This reaction has a much larger energy of activation barrier than the previous reaction that we did. By about double. Here you can determine the energy of activation and the frequency factor. We've already done an energy of activation, so I want to do specifically the frequency factor. Again, you have to realize that y equals mx plus b is the natural log of k is equal to a negative e sub a over r times 1 over t, which is our x, plus the natural log of the frequency factor. So in other words, the natural log of the frequency factor is equal to 26.8. The inverse of natural log is exponential, so we're going to take exponential of both sides. And you get A is equal to E to the 26.8. So our frequency factor is 4.36 times 10 to the 11 per second. That's how many molecules approach the top in a given second. Folks, if you haven't figured it out, I'm just using the equation from the graph and understanding the equation of a line and plugging the two in as appropriate. I'm going to just introduce the next equation, but we're not going to use it. We'll pick up with this on Tuesday. And that is, we can also do a 2-point Arrhenius reaction. This one allows us to determine, again, a variety of options. The two-point Arrhenius equation is natural log of K2 over K1 is equal to negative E sub A over R times 1 over T2 minus 1 over T1. Folks, this equation looks identical to an equation we did previously. Except in our previous one, we were dealing with a 2-point vapor pressure. And when we dealt with the 2-point vapor pressure, our slope was equal to negative delta H of vaporization over R. But there is a lot of similarities between these two. So in other words, the math is going to be similar. And we will pick up with an example on Tuesday of next week. I will see you Monday for the kinetics lab, and I will not have much discussion prior to starting the lab. Yes.
So I heard you had the exam to be next Tuesday.
Not the next time I see him, but the one after.
Yeah, the one after. So a week from next week Tuesday.
Yes.
Okay. What happens do you plan to cover so far?
So as of right now on the test, what I'm expecting is to start with section 13.5. And if you want to write it down, I don't need that anymore. If you need to write it down.
I guess. Yes.
13.5, and I am expecting to for the exam to go through. Come on, Faith. Where's your hand? Why is your hand's not working? 15.5,
to 50.5.
which is 100 pages.
Okay. Okay.
So I basically plan to get through developing the equilibrium constant for heterogeneous equilibria.
Mhm.
I am skipping one of those sections. I'm not doing the difference between KP and KC.
Mhm.
I'm just out of time, and I've got to cut something here and there. And that's one of the things I'm gonna cut.
Okay.
But I do expect to do most of the rest of it.
Mhm. So equilibrium of heterogeneous, what is that?
That is where
Really?
if you have a solid, a liquid, or a
Oh.
pure, you don't include pure solids and pure
Yeah.
liquids.
Yeah, okay.
You just include aqueous and gases.
Okay, so that chapter is gonna be setting up an equilibrium constant? Or is it just describing?